Today we have talked about GraphSAGE. GraphSAGE is an inductive graph neural network which uses sample and aggregation method. It performs better on the dynamic graph because it uses samples and then by doing something it inform for the on-scene data. So this data is already there, but during training we get this type of data. So initially it's not there. Initially these three we trained on these three data, so we don't have the information anything about this data in the GraphSAGE. Obviously we are talking about. Initially we have these three data, and later after the pre-training and training we get this type of information because it uses sample, like we can get its sample, neighborhood sample, and after that we inform from that, so it will try to approximate these values. Approximate means like we get about 90% accuracy, so we will try to predict. So here we see how. Here we will see pattern halves and pattern samples. So here you can see in this pig, in the k equal to 1 means half equal to 1 means this red nodes first neighborhood, like this 5, this node, this node, and this node. These are the neighborhood of the red node where k is equal to 1. So its first neighborhood means its k half equal to 1 means its immediate neighborhood. When we say k equal to 2, red node's second neighborhoods are included. Like here you can see this node, this node, this node, like within this circle. And here we can see some of nodes are like aggregated. Like here you can see this. So it uses samples. Some are red and some are highlighted. The highlighted nodes are the sample nodes. Like we consider we have taken a specific iteration on a specific sample. In specific iteration we may have different samples, like let's say we take in 1000 iteration, let's take we have taken like 4 or 5 this type of samples. It will sample. We will see how it will sample. In this sample, it uniformly samples from its neighborhood. Like here we have maximum, we say have 3, so it will only take 2 to 3 which are possible. Yeah, so here we see how these are aggregated, like from this node to this node information is calculated on this, like aggregated on this node's information in this node, and finally we get these 3 nodes aggregation in this red node. So that's the overview. Now we will talk about that, like how it's the background, and first we will talk about its embedding. What are its embedding and how we generate them. assumes the embedding are already trained and parameters are fixed. Like we say, let's say we have a text data, so we do its embedding like some external or what to vec type of generator or sentence to vec. This type of embedding we do, and after getting the embedding, we will pass this embedding to the GraphSAGE for the processing. Assume that we have learned the parameters of the aggregator function as well as with respect to matrix WK. So it's a generated one, but our initially embeddings are we get from the external embeddings. We use uniform distribution to sample from the neighborhood. So this is its forward algorithm, like how we have calculated. So let's say for each iteration we get HP0 for its initially embedding, which is XB, like we already get the embedding. So here is XB for k equal to 1 to k, like how many aggregators we use. This is we loop through aggregators, and again we loop through nodes like sample nodes. Then we update our embedding by aggregation function with its previous embeddings, like which are neighborhood of this node. And again we will pass into nonlinearity, and we concatenate this embedding and its previous embedding. And we also learn the WK, like for a learning parameter for each aggregator. So after that we normalize, and in the end we get our Z, our final embedding, parameter learning. So how we will learn our parameter? For the predictive, we can use fully unsupervised. Sometimes we can use supervised also. So let's see how it's done. Here is the loss function, like jg of z of u, like our final output ZU will be equal to minus log of sigma. Here we can see sigma is sigma ZU transpose into ZV minus Q into e to the power Vn, like log sigma into ZU transpose ZVn, where E equal to co-coordinate U in the fixed random walk, like we have talked about in previous video. What is random walk about? So, like random walk of fixed size, and we have taken sigma function Pn negative sampling distribution, Q number of negative sample, ZU that feed to loss function. And here the important part is A into Pn of V is Euler's constant for this node of V and the negative sampling distribution of V. For the experiment purpose, we have taken three types of aggregator functions, like to get which can perform better. First we take mean aggregator, like where as our embedding will be embedding for V in the for kth aggregator will be sigma nonlinearity W into mean of like its previous embedding in and its neighborhood nodes previous embedding. So like here we can see better. In embedding we have taken like this is we are calculating for this nodes embedding, so we calculate its embedding like this nodes k minus 1 embedding, and we calculate this node and like we calculate its all the k1th aggregator. So we aggregate these three and take its mean. Like we add these three, like we have taken these three nodes what we say mean and aggregate into that object. Like we have taken these nodes k minus 1 again. I am making it clear again. We have taken these nodes previous steps like k minus 1 step. Here don't confuse with this k is hop. So we have taken these nodes previous embedding and these three. We take these 4 nodes embedding. 4 nodes means its previous steps out. So these 4 nodes and calculate its mean in the mean aggregator. And again in the LSTM aggregator we adopt LSTM to separate on the unordered set by simply applying LSTMs to a random permutation of nodes neighborhood. Like we apply LSTMs to its random permutation, like sometimes it's any random permutation we apply LSTM on its neighborhood. Like we apply here LSTM aggregator to get this, like any random type of LSTM on these 3 nodes. Like we apply and aggregate pool aggregator of k into pool, so it's equal to max of sigma into W pool, which is learnable parameter, and plus beta, which is bias. So where Ui belongs to neighborhood of V. So here we can say we taking this mass. Like when we explain it will be if it's V, its Ui will be this. Like we apply Ui into some learnable parameter into this and takes it marks and update this value. So that's how pool aggregator works. Experimental setup. For the experiment, we have taken a random forest classifier, a logistic regression that ignore graph structure, the deep work algorithm, representative factorization based, and a concatenation of the raw features and deep work embedding for comparison. Then we use Graph Convolution Network, like the supervised version of equation 1. Equation 1 we have taken to this, like loss function. This is GraphSAGE GCN for the unsupervised version. For supervised version, we train on the cross entropy loss. and GraphSAGE with different aggregators. Like for we have taken different type of the variation in GraphSAGE, like we have sample and aggregate. After that, for the downstream task, we use a random classifier, a logistic regression, the deep work algorithm, and a concatenation of the raw feature and the deep work embeddings for comparison. And also we have taken GraphSAGE Graph Convolution version, which is unsupervised. If you talk about unsupervised, it will be of like optimizing this loss function. For the supervised, you use cross entropy loss and GraphSAGE. These are the experimental setup. And for the data, we use these three. I am going quick through into that. So if you want to know more, you can pause and read about it. So we have taken citation data and Reddit data. These are two huge graphs, like embedding like Jensen, like this, and this is three-dimensional like vectors. These two are vectors, like this is generated, it's initially embedding generated in GenSim, and its initially embedding is generated in this blob common crop vector for feature. And this is a protein-protein interaction. It is like the graph contain like this number of nodes. This is after stick. And citation and Reddit data are two evolving graphs, like dynamic graphs. Like in the previous video we have talked about dynamic graphs, and here also we have take some example of dynamic graph, like how it can solve the dynamic graph problem for the unseen nodes. In the dynamic data, we get unseen nodes, and in by sample and aggregation, these GraphSAGE can solve this type of challenges. Results of three datasets are given in the F1 score. F1 score is composed of like recall and precision, which is equal to tau into recall into precision divided by recall precision. So basically F1 score is a good good measure for its accuracy, because taking both precision and recall. So we have seen the result, like they have shown the result in the form of F1 score. So here we can clearly see GraphSAGE LSTM and GraphSAGE pool perform most of the tasks efficiently. Like here we can say GraphSAGE GCN perform better, but in the unsupervised version and in the supervised version, GraphSAGE LSTM and GraphSAGE pool perform much better. So here is the time taking. So here you can clearly say deep work version take much time, but when we have taken in the paths, it will much reduced. You can see GraphSAGE GCN take full dataset with 10 seconds. Here you can see runtime versus its F1 score, micro F1 score. see, we will say this is a better runtime result. Like this taken much less time and we have gotten much accurate score. So that will be an ideal. Now we have talked about some advantages of GraphSAGE. Unlike Graph Convolution Network, which is destructive, means it only works on the stable set of nodes, or you can say graph. GraphSAGE can generalize to unseen nodes. Like we have seen in this video, the GraphSAGE is all about generalizing the unseen nodes. So there are six main highlighted advantages of the GraphSAGE. Only a fixed size subset of the neighborhood is sampled, which reduces the memory and consumption. Which, like memory size and consumption, is reduced due to its sampling purpose, like sampling method. Support different aggregator function. In the paper, they have taken GraphSAGE with mean aggregator, LSTM aggregator, and max pool aggregator. So, if we have seen various this type of aggregators here. Learns how to aggregate local neighborhood information, enabling robust feature learning for downstream tasks. So, this also use learnable parameter aggregate. So for the better aggregation method, so there are also advantages since it avoids full graph computation. It's easier to parallelize on GPUs and its distribution. So let's say how it is useful, like how it will perform better in the GPUs. Let's say GPU have many threads. Let's say these two are of some threads. These two are some threads of GPU. Let's say like here we have taken these three nodes as sample, and these three nodes are fed into this, and let's say we again take change the color. We again take this node, and this node as sample. So these three nodes will be fed into this thread. So this thread can run parallelly. This is how we use GPU to parallelizable, like with graph parallelizable. With data, we parallelize graph in GPU by providing different set of data. We parallelize the computation. Disadvantages: only local neighborhood are sample and aggregate. Like I have said this in the previous video. Let me remind you again. When we talk, it's only take its like k hop. It's let's say we take 1, and sometimes we take 2. Maximum we take 3. Like 4. Like to avoid oversmoothing. So this will only take the neighborhood information, and let's say we have a much further node which may be important to to the node which we are interested in, but because it's too far, we cannot apply or extract this information into our interested node. So that will become disadvantages. The random sampling of neighborhood can lead to noisy or unstable representation, especially when the sample neighborhood are not representative of full neighborhood. So we have taken a sample and we can infer from that data to what its result would be. So it may contain some bias, like it may not represent our sample may not represent the whole data. That's a statistical issue. So that will be a problem. With more layers, there is risk of oversmoothing, like we have said. Due to repeated sampling across batches leading to redundant computation. Let's say sometime we take these three nodes, like we have taken these three nodes, and there is also a chance that we may take the same three set of nodes again. Sometimes there are like some samples, let's say of our sample size is fixed of k size, or let's say for example we take, let's say it's 3, our sample size is 3, and in the first batch we have taken these three set of node, let's say x, y and z, these three set of nodes, and there is a possibility of that by we are doing like the batches and we parallelize this thing. So there also would be a case, there also would be a sample which take these three exact nodes for its calculation. So that would be redundant because we already have taken these three. So there are some disadvantages. In dense graphs, sampling introduces high variance and can skip critical connections. Like we may have connections which are, let's say we have dense graph. So sometimes there is possible that our whole sample cannot get the much information, or it will get high variance, like say it's also a statistical problem. These disadvantages will be our building block for our next models, like graph neural network models. Like it will be a graph, it will be a gap that we can cover. So from previous video we talk about Graph Convolution Network, which cannot perform better the dynamic graph, and here we have seen how we come up with better model that will improve the result, or you can say generalize the dynamic graph nodes. Like for the unseen node, we can generalize. Introduce a good approach that allows embedding to be efficiently generated for unseen nodes. The whole point of the GraphSAGE is it can generalize the unseen node. It's the most important part of the GraphSAGE. GraphSAGE consistently outperform the state-of-art baseline graph convolution network, effectively trade off performance and runtime by sampling node. GraphSAGE outperform the state-of-art baseline. is introduced by Graph Convolution Network for the graph learning. Okay, let's talk about summary. First, we talk about what is GraphSAGE. After that, we have talked about what are hops, like how we aggregate in the GraphSAGE. Then we talk about its embedding. After that, we talk about how parameters are learned, like for the unsupervised we take equation 1, like JW, remember like JW, and for the supervised we take cross entropy loss function, and for the embedding part we have taken some previously embedded vectors in the input of the GraphSAGE, and we have seen the algorithm, and after that we have seen the data. After learning process, we have seen its experimental setup, which contains like 3 types of aggregators, like mean aggregator, LSTM aggregator, and pool aggregator. After that, in the experimental setup, we have seen different models for the downstream tasks. First, we have talked about random forest classifier. After that, logistic regression, and a deep work-based framework, and also GraphSAGE GCN, which is unsupervised. We have taken equation 1 to optimize its result. After we take like GraphSAGE with these 3 type of aggregators, like mean, LSTM, and max pool aggregate. After that, we have seen its result, and after the result, we have talked about some of its advantages and some of its disadvantages, which will be our building block for the next paper, or you can say model, in the graph neural network field. So in the next video, we'll talk about graph retention network, like GAT. So thank you. That's it for today.